Hey everyone, this is Adam, and today we're going to be working with the composition of reflections in 3 concurrent lines. This is going to be supplementary to the lesson I'm going to be teaching on Friday, March the 9th. However, even if you have watched this video before you've seen my lesson, or if you've not read 6.1, it should still make a lot of sense, as a lot of the things that we're going to be doing in this construction are fairly intuitive or things that we have actually done before. So we're going to go ahead and jump right in. We're going to be working on problem 9 out of chapter 6.1, which is going to be, suppose x is perpendicular to y and k makes a 45-degree angle with line x. Prove that the composition of reflections of the 3 lines can be expressed in a single line and find that line. And then in B, we're essentially going to take that and we're going to find the generalization of the result. And we're going to show that for any 3 concurrent lines, we can show that the composition of their reflections can be expressed in a single line. We're going to go ahead and jump over to GeoGebra. So as we stated, our first problem that we are interested in is finding a perpendicular line, a pair of perpendicular lines, and a 45-degree angle to those lines. And then we are going to go ahead, we will rename these x, y, and k just for continuity's sake with the problem that was described. Alright, now the first thing we're going to do is we're going to demonstrate the image of some arbitrary point under the composition of the reflections, reflection of y, of reflection of k, of reflection of x. Just a reminder that when we are actually going to be forming this image, though we are going reflection of y, of reflection of k, of reflection of x, just remember that we are actually going to be performing those reflections in the opposite direction in order to get the point that we want. Go ahead and use our reflection tool. We reflect C about x, C prime about k, and C double prime about y. Now we can also go ahead and hide these 2 points just so they don't get in the way or cause us any confusion. Now, intuitively, we can look at this and say it looks an awful lot like C is just being reflected across the line K to be equal to C triple prime. This is in fact the case, but we're going to show that in a more rigorous way other than just saying that K is the perpendicular bisector of the line C and C triple prime. In order to do this, we are going to first need to look at the composition of the reflections, reflection of y, of the reflection of k. And we are going to take advantage of the fact that for any composition of 2 reflections, we can find an equivalent composition of 2 reflections using any line we want as one of the 2 reflections. And why this matters is because it's going to allow us to perform a trick, which I'm going to talk about in my lesson on Friday, which is essentially that if we find a composition of 2 reflections, where the second reflection in that composition is x, that is equivalent to the composition of the reflections of y, of the reflections of k, we are allowed to substitute that. What that will allow us to do is essentially say that the composition of y, of the composition of k, of the composition of x is equivalent to the composition of some line j of the composition of x, or of the reflection of x of the reflection of x. As we have seen before, when we have reflection of x of reflection of x is actually just equal to the identity matrix, or rather the identity. So what that's going to allow us to do is to find out that line of reflection j is actually equivalent to the composition of each of these three reflections. And all that we have to do in order to find J is to demonstrate that the reflection of Y of the reflection of K is equal to the reflection of J of the reflection of X. So we can go ahead and try and locate that now. As we said, we are starting with some point C. We would reflect first about the point K. As we can see, our intuition was correct. C triple prime is in fact just the rotation or reflection of the point C about the line K. And we can then take that point and reflect about the line Y. Now, we have the mapping of C to D under the composition of the reflection of Y of the reflection of K. What we can do now is we know that we want a composition of the form reflection of J of the reflection of X. So we can reflect first about the line X and know that our next line that we create is going to be J, and it needs to map C'2 to D. Lo and behold, if we are to connect D with C'2, we see that yes, in fact, if we take the midpoint of this line, it intersects with the line K, and if we take the perpendicular line to D C2 prime through F, it is in fact equivalent to K. What this essentially means is we have shown that the reflection of some arbitrary point C about the line K is equivalent to the transformation of C under the composition of reflections Y of K of X. And we can see that this point holds true no matter where we place C. This point C triple prime and C prime 1. 1 is the reflection of C about the line K, and the other one is the transformation of C under the composition of reflections. As you can see, no matter how we move C, they move together, demonstrating that yes, in fact, the line K is the proper equivalence, and that the composition of Y of K of X can be expressed as just the reflection about line K. Now, while this is interesting, we can also show that it is true in the general case. So what we're going to do here is largely the same process, except instead of having specific angles, we are going to go ahead and make them general. So that is, we have 3 concurrent lines at a point, and we are interested in finding the composition of H, of G, of F. So we have some arbitrary point here, call it E. We can find its transformation under the composition of these 3 reflections, reflecting first about F, then about G, and then finally about H. And again, we will get rid of these extraneous points just because they are not really necessary and we don't want to confuse anything with what points are what. In this instance, E is going to be the original point and E triple prime is going to be the image under the composition of these 3 reflections. So just as we did in the last problem, we can go ahead and say that we are interested in finding a composition of 2 reflections which is equivalent to the composition of the reflection of H of the reflection of G. And we want that to be of the form J, the reflection of J of the reflection of F. By doing that, we'll be able to perform the same trick where we cancel out the 2 transformations of F, forming the identity, and are left with just a single matrix, or a single transformation that is equivalent to the composition of these three reflections. So we can start by finding the image of E under the composition of H of G. So we're going to go about that first by reflecting about G. And as we can see here, it is not always the case that G, or the middle line, is going to be our solution. That was unique to the case where they were 45 degrees and then 90 degrees apart. We'll see here that we actually do have a separate line, which we'll call E1, which we will then reflect about H. We will get rid of E1 just, again, so we can better make sure we know what is going on in this system. As we can see here, this is going to be our image under the reflection of H of the reflection of G. And now we know we want another composition of reflections, reflection of J of reflection of F, that also maps to F. What we're going to have to do for that is we're going to map E first across F, reflect across F, we get E2 prime, and then we need a line for which we can reflect E2 prime across, and it will equal F. Just as we did in the last problem, we're going to go ahead and segmentize that. We are going to find the midpoint, and then we are going to take the perpendicular line through G, perpendicular to the segment connecting F and E2 prime, and lo and behold, we have our line J. We'll hide this and hide G just to get it out of the way. But we have our line J now, and we can conclude then we know E triple prime to be our reflection under the composition, or our transformation under the composition of these three reflections. And as such, if we take E and we reflect it across J, it is equivalent to E triple prime. As such, J is going to be our solution, and we can also show that this is not unique in the sense that it's only these specific angles. We can see that no matter how we move E, the reflection about J and the transformation under the composition of the three reflections F, G, or H of G of F stay the same. They are thus equivalent. We can also see that even if we move these angles, the points still move together. Thus, in general, we are able to conclude that for any three concurrent lines, the composition of reflections about those three lines can be expressed in some single line. Thanks so much for watching. I really appreciate it. Hope this was helpful for you and may tend to build off of anything that you may have learned from my lessons. Thanks so much. Bye.